Hi, my name is Joshua from TAG. Welcome back to the second part of the video series on matrix operations in R. So we stopped at the level of crossprod in the previous video, and I gave an explanation, and I also differentiated the difference between crossprod and the normal multiplication of matrix in R. So let's have an example of the normal multiplication. Let's go back to our editor pane, Ctrl+1, and then let's have the normal multiplication in R, which is quite different from this column wise multiplication as we have explained in the previous video. So to multiply two matrices in our programming, you use this percent multiplied by percent, and then we are multiplying it with C. Don't forget the condition for us to multiply the column of the first matrix, which is A, must be equal to the row. The value in the column of the first matrix A must be equal to the value of the row for matrix C. So if I run this, the result is out, and I can easily see my answer as 7, 15, 23, 10, and 22. So having done this, we spoke about dimension to explain the condition, and I said dimension of A, and then semicolon. I can go ahead and say dimension, my system is a bit slow, dimension of C, and so I can run both, and you could see the dimension is for A is 2 by 2, 2 by 3 for C, and you could see the condition for that of the column is 2, and the row for the other one is 2 also. So we have a matrix where we have the resulting product between the two of them to be 2 by 3. So the cross prod we started the last time is quite different. For instance, if I say cross prod and I use A, C, and I run this, the result is going to be different, though they will be of the same dimension with the resulting matrix we get after multiplying A with C, but they are just going to be different in terms of the elements. So what is going on with crossprod? What is going on with crossprod is what we are doing is we are doing the transpose of A, and then we are multiplying it with C. That's what is going on. So what exactly do we mean by transpose? Let's have A. Let's print out matrix A. This is 1, 2, 3, and 4. So what is happening is that what we have as our column in matrix A, if I take the transpose, what we have as our column, everything we have here, this 1, 2, this 1 and 2 will be what we will now have as our row if I take the transpose of A. So to take the transpose of A, it's simple. In our program, you just press T, and then you put the matrix as the only argument, and so you say A. So if I run this, you will see what is happening. The transpose of A is 1, 2, 3, and 4. So the row turns to the column, and the column turns to the row. That is just what is going on when you take the transpose of a certain matrix. So when you take the transpose of this matrix and then you multiply it using this percent multiplied by percent, and then you multiply it with C, that is what we are doing each time we talk about the concept of crossprod. So we have talked about diagonal, but I'm going to revisit the concept of diagonal again before I lead us to determinants. So if I say diag of A, I can extract the diagonal, and then I have it as 1 and 4. If you check matrix A, I have explained the concept of diagonal in the previous video. This is it, 1 and 4. This slant line cut between the matrix 1 and 4. So it's also possible, like I said in the previous video, that you can have diag, and then I'm creating a square matrix that has 3 rows and 3 columns, and I want to create like a diagonal with 1, 1, 1, 1, 1 on its diagonal. This is also called an identity matrix. So if I run this, I have this identity matrix with 1 on its diagonal, 1 all through the diagonal. So this is an example of an identity matrix, and the example we are showing is the diagonal where we have 1 1 1. So having done this, let's talk about the determinant. Let's talk about determinant. So if I'm going to say the determinant of A is going to be the diagonal minus the order multiplication of the rest column and the row. So this is what I mean. So if I say det of A, determinant, it's from the package matrix. So if I say det of A, let's run it and let's see what will happen. So I have -2. How do I get -2? It's very simple. What is the diagonal? Let's run A. Let's run A again. So what we are doing here is 1 multiplied by 4 is 4. So this is the diagonal. We are going to multiply the two elements that forms the diagonal. 1 multiplied by 4 gives us 4, and then 4 minus 2 multiplied by 3, 6. If I run this, Ctrl Enter, you will get -2. Let's take again the determinant of B, which is also a square matrix, and let's run it. We have -2 again. Let's see B. So this is B. 5, 6, 7, and 8. 5 times 8, we have 40. Now, minus 6 times 7, 42. So if I say 40 minus 42, and then this is the result, -2. So that is how we get the determinant of a certain matrix. And why are we doing some of these things? Is because I would also talk about the concept of adjoint, the adjoint of a matrix, as we proceed in this particular video, the concept of adjoint. But before we go into adjoint, I'm going to load a library called mass. I'm going to load a package, called mass. By default, it should be there. So I'll just load this particular package called mass. The essence is I want to use a function from that package called J-inverse. So this J-inverse gives us like a generalized inverse of a certain matrix. So it calculates the more Penrose generalized inverse of a matrix X. So if I say G-inverse and I say G-inverse and I put A, so this is the inverse of matrix A. This is the inverse of matrix A. So how do we get the inverse? So I'm going to provide a formula that would make this whole thing very easy for us to get the inverse most times. So the inverse of, I'm going to use this formula, the adjoint of A, I'm going to say equals to the determinant of A multiply by A inverse. Let's say inverse like this of A. So if I'm going to get the inverse of A, so inverse of A, invariably inverse of A will now be adjoint of A divided by the determinant of A. So which is the same thing as adjoint of A times 1 over the determinant of A, the same thing. So we have the understanding of how we can get our determinant, and at the same time we have an understanding of how we can get our inverse. So it becomes very easy for us to calculate the adjoint of matrix A. So for instance, if I'm going to get the adjoint of matrix A, I'm going to say adj like this. I can just store it and say adjoint of matrix A, and I said determinant of A, and then I'm going to say multiply. Let's see what is going to happen. Let me try column wise multiplication. Determinant of A multiplied by the inverse, G inverse from the mass package, and then I put A. Let me see what will happen, and then let me print ADJ and see the resulting. So this is the adjoint of matrix A. So this is just very simple. The adjoint of matrix A is giving us a square matrix again with element 4, -2, -3, and 1. So don't let us forget that particular formula. The adjoint of a matrix is equal to the determinant of the matrix multiplied by the inverse of the matrix. So with arrow programming, all this becomes very easy. Before I go, I'm going to talk about some other functions we can use when working with matrices in R. One of them is this solve function, solve, coming from the base package, and what it does is a generic function that solves the equation A multiplied by X equals B for S, where B can either be a vector or a matrix. So one of the conditions is that this is what we are doing. In some situations, we have a matrix A, which must always be like a square matrix, multiplied by X, which is unknown. We don't know S, we are solving for S, equals to B. So this B can either be a matrix or it could be a vector. But ensure that if it is a vector, let it be of the same dimension with that square matrix. Either meeting up with 2, if it is 2 by 2, if it is 3 by 3, the length must also be in line with the dimension of the matrix. So what we are going to do here is this. Imagine you are looking for S. What you would have just done would have been S equals B divided by A. So S invariably would still be B. So when you have it this way, you can say B times 1 over A, 1 over A. So X can also be B multiplied by the inverse of A. So that is what the solve function from that particular base package is doing. So I'm going to turn this whole thing again to comments, and then we treat the example, then I proceed. So then if I say, let's create like BR, I'm not going to call it B, I'll say BR, and then just call it 1 and 4, and then I store this as a vector, and then I already have A. Let me run it again. This is what we have as a square matrix. So if I say solve A, comma BR, so this result 4 minus 1 is obtained in this particular dimension, B multiplied by the inverse of A. Because what is going on here is, don't forget, this is A multiplied, we're using this multiplication, matrix multiplication, times X equals B. And so that was the equation we rearranged to get what we have in line 35. So having done this, I will just talk about the possibility, this particular function, and this will be where I will stop. Okay, before I do that, let's talk about this summation of the column and the summation of the row. You take the sum, you can also take the mean. So let's say this is A, again I'm running it. So if I'm going to take like the row, the sum of the column, like 1 plus 2 is 3, and this 3 plus 4 is 7. So I can say colSum. It's a function we use majorly when we are dealing with chi-square analysis. If you want to do it like in a way that you want to teach people to understand it, so you use some of these functions, colSum of A, and if you run it, you see 1 plus 2, 3, 3 plus 4, 7. So you can say rowSum, and it will be 4 and 6. So if I say rowSums of A, and then I run this, you understand how we have 4 and 6. So the same thing, you can say colMeans. You can say colMeans, and you say A. So it's like 3 divided by 2, we have 1.5. 7 divided by 2, that is like 3.5. So you understand rowMeans of A, the same thing. This is like 4 divided by 2, 6 divided by 2, which is 6. So the last thing I'm going to talk about is this concept of C-bind. So I can bind a matrix together that are of the same dimension. So if I say C-bind, column bind, and then I say A, comma B, look at this, what's going to happen. So I binded them together by column. They are of the same dimension, 2 by 2. At the same time, I can bind them again together by row and say A, comma B, and run it. So you could see this is the result we have. We have matrix A on the top, and we have matrix B underneath. In the case of the column bind, this is matrix A, and the result of matrix B is just combined with it. So like what we have been doing so far, we have been using matrix to like matrix function to create a matrix from scratch. So if you check the class of A, it tells you it's a matrix or an array. So the same thing, you can create a matrix by combining two vectors together. So if I say vec, and I say this is, I think I've talked about this. So if I say 1, 2, 3, and 4, and I run this, and I say vec 1 again, and I say 5, 6, 7, and 8, and I run this. So using this cbind, arrow bind, I can combine them together to form a matrix. So I can say vec m, vec matrix, and then I can say cbind, vec, and vec 1. So if you check the class of vec m, it tells you it's also a matrix. So when we proceed, I will explain to us one of the reasons why we always do like initial data analysis, like why we always do some diagnostics before we go into our analysis. So at this point, I want to appreciate you for choosing to learn R with me, and I believe you've learned something from this particular tutorial. Do have a great day. God bless you. Bye bye.